In this section, we're going to continue on with learning some different approximation methods. Today, we're going to focus on the midpoint Riemann sum and the trapezoidal sum, and you'll find that these are actually better approximations, more accurate approximations than the left or the right were giving us in the previous section. To begin this, let's start with a review of what we've done previously. The left and the right Riemann sums is what this warm-up entails. So maybe go ahead and give this a pause and see how you do on these. These left and right Riemann sums are just a way to approximate an integral, which is the area between the graph and the x-axis. You can sketch this out if you want to, but you don't really need to. What we do is we look at the distance of the interval, and then we multiply times the number on the left side, and that gives us the height of that rectangle on the left side. So the first rectangle is 1 by 1, and that's this part. And then rectangle number 2, it's going to be a 1, because 1 to 2 is a 1 unit, times the height on the left side, which is the 2. So that's a 1 by 2. The third one is 1 unit across, times 5, so it's a 1 by 5. Rectangle number 4 is a 1 by 10. Because all of these rectangles had the same base length, because these were equal subintervals, you could just take that 1 and factor it out. It's kind of irrelevant that it's a 1, but just keep in mind if you have equal subintervals, you can factor it out and get a final answer of 18 for my left Riemann sum. It would be acceptable to start with that second step if you recognize that you have equal subintervals. So I'm looking here and I see there's 1 unit in between all of those. Then I could do this right Riemann sum by writing that equal subinterval out here initially, kind of like how I did with the 1 over on the left Riemann sum, and then just multiplying times all the heights that happen on the right. So the 2, the 5, the 10, the 17, add all those together, and I get a final answer of 34 for my right Riemann sum. It appears that my left approximation is under and my right approximation is over. So to balance that out a little bit, in part 3, question 3, we're going to do an average of the two. Averaging the sums gives me 26, and this would be a more accurate representation of that integral than either the 18 or the 34 alone. And there is a nice tie-in to one of the new sums that we're doing today. In the first one, we're going to use what's called a midpoint Riemann sum to approximate this integral. I'm using the same function that we were using on the warm-up, so you can compare how all of these answers relate to one another. In this one, I'm going to approximate that integral using what's called a midpoint Riemann sum with 4 subintervals of equal length. My first job is to split the region into these 4 subintervals. To find the length of each subinterval, you could always take your limits and subtract and go 4 minus 0, and then divide by however many intervals you want. And that gives me 4 over 4, and that tells me that the length of each subinterval is going to be 1. So here each subinterval is 1 unit wide. Some problems are easier to find how you split it up than others, but always keep in mind you can use this formula up here if you need to. When you do a left Riemann sum, you travel up the left side, hit the graph, and cut over, and that's where you draw the tops of your rectangles. If you're doing a right Riemann sum, you would travel up the right side, hit the graph, and then cut over, and that would be where you would draw the top of that rectangle. For a midpoint Riemann sum, we're going to travel up the middle of each of these intervals. So I look at between 0 and 1. The halfway point is 1/2. So 1/2 or 0.5. I go up at that value. I hit the graph. That is where you draw the top of your rectangle. And my next interval goes from 1 to 2. Halfway in between is at the 1.5. I go up at the 1.5. I hit the graph. That tells me where to draw the top of the rectangle. In between the 2 and the 3, the midpoint is a 2.5. I go up at the 2.5 till I hit the graph, draw the top of my rectangle. And my fourth interval, the midpoint in between 3 and 4 is 3.5. So I go up at the 3.5 and draw the top of my rectangle there. So here are my 4 rectangles whose areas I need to find and add together. Right away, it should appear to you that this approximation is better than either the right or the left alone, because for every area that I'm including that's actually above the curve that shouldn't be included, there's an almost equal area that balances that out that's being missed. And that appears here as well. So I'm including this little chunk in my approximation, and it's balanced out by this little chunk that isn't included. So for every area that I'm including in my estimation, there's an almost equal area that's being left out, and they balance each other out and actually make this a pretty good approximation for that integral. So basically all I need to do is find the area of 4 rectangles. Rectangle number 1 goes from 0 to 1, so it's 1 unit wide. Its height is found by plugging that 0.5 into my function x squared plus 1. Rectangle number 2 also has a base length of 1. Its height is found f of 1.5. Rectangle number 3, 1 unit wide. Its height is found by finding f of 2.5. Rectangle number 4 again is 1 unit wide, and its height is found by finding f of 3.5. Now I'm just going to use a calculator to plug each one of these values into my function that's given. That gives me a final midpoint approximation of 25. Notice that it's pretty close to that left and right Riemann sum average of 26. We've got one more approximation method to look at that's going to use trapezoids instead of rectangles. We've got our same function, x squared plus 1. We're still going to use 4 subintervals, and we're going to use trapezoids this time to approximate that area. In doing this, we're going to develop what's called the trapezoidal rule. There's some conditions on using it, but we'll go through that as we do these trapezoids. The first step looks the same for all of these. You take your region and split it into the indicated number of subintervals, and I have done that. With trapezoids, just as the name implies, instead of drawing rectangles, we're going to be drawing trapezoids. I'm going to use these parallel divisions of my subintervals as the basis for my trapezoids. And connecting consecutive vertices is going to close those figures for me. And you can see right away that this estimation is going to be pretty close to that actual area. It's not quite the exact area, and we'll look at over and under approximations like we did with the left and the right in a minute. But what you should see is these trapezoids pretty closely approximate the area that I'm interested in. I've got 4 trapezoids that are formed, 1 for each of these subintervals. I just need to find the area of each one using our trapezoid area formula that's over here on the left. For trapezoid number 1, my height is going from a 0 to a 1, so it's got a height of 1. Its bases, I need to look at the parallel sides. Don't trust the graph. What we want to do is use our function to find those lengths. When I plug a 0 into my function, I get a value of 1, so this base here on the left is a 1. Here at when x equals 1, when I plug a 1 in, I get a 2, so it's going to go up to a height of 2. Trapezoid number 2 also has a height of 1. We're going from 1 to 2 on the x-axis, so the height is a 1. This base right here is actually this 2 that I found here. And here where the x is 2, I can plug it into my function and see I reach a height of 5. Trapezoid number 3 also has a height value of a 1. I'm going from a 2 to a 3, so it's got a height of 1. This base is when the x is 2. I've actually already calculated that when I came up with this 5, because that was the base of trapezoid number 2 as well. Going up at the 3, the length of the base on the right side is 3 squared plus 1, or 10. Trapezoid number 4 has a height from 3 to 4, or 1. The base on the left is the height when x is 3, which is this 10 I already found. And on the right side, when I plug in a 4, I get a height of 17. You could calculate all these numbers, and that's going to be your trapezoidal approximation for this integral. I'm trying to develop a rule out of this, so I'm going to play around with these numbers a little bit. What I see first is that of my 4 trapezoids, they all have a 1/2 and a 1 in common. The 1/2 is part of the formula, and the 1 is the fact that they all had a common height of 1. Because they have that 1/2 times 1 in common, I can factor it out. What's left are just the numbers, and I left them unadded to make a point with it. What you can see happening is a repeat in some of the numbers. The base of a 2 for trapezoid number 1 was repeated in trapezoid number 2 because in the graph you can see they share that base. It's a common base to trapezoid 1 and trapezoid number 2. Ditto for the 5. The 5 is a base here for trapezoid number 2 as well as trapezoid number 3. And this base of 10 is a base of 2 trapezoids as well. So what we see is anytime we have an interior base, it is shared by 2 trapezoids, therefore it appears twice when I'm doing this trapezoid formula. And that allows us to develop a rule out of this. And this is our trapezoidal rule. The h was just that common height that they had, that 1. The first base and the last base are just taken once because they are used only by a single trapezoid. But each interior base is doubled up, and there's no limit to how many you can have. That's the ... in here. And this is our trapezoidal rule. What allowed this to happen was the fact that each of my trapezoids had the same height, in this case 1. It doesn't always happen that way, but if it does, you can use the trapezoidal rule. If you do not have equal subintervals, then you're not allowed to use it. So here's the requirement for using the trapezoidal rule. You must have equal subintervals. You don't ever have to use this rule. You can always do like we did in the beginning and just find the areas of each individual trapezoid. The answer to this approximation ended up being 26. And you will notice that the answer to number 3 in the warm-up, that average of the left and the right, was 26 as well. We're going to talk about this further in class, if that is coincidence or if there's a reason that that happened. Let's go on and take a look at some examples. And this is going to review you over all of our Riemann sums. For this first group of questions, I have a table of f of x values. F is continuous. In part A, I want to find a left Riemann sum to approximate that integral that goes from a 1 to a 9, and those are the values of the table, so I'm going to include the whole table. I have 4 subintervals indicated by the data in the table. Just means that these are divided for me. So from 1 to 3 is the first, 3 to 5, 5 to 7, 7 to 9. Because I have all these equal subintervals of length 2, I can shortcut this left Riemann sum a little bit and factor that 2 out and multiply by just all the heights on the left side. So basically I'm doing 2 times 6, 2 times 8, 2 times 4, and 2 times 5. I have just factored that 2 out, and I get an answer of 46. Part B is a right Riemann sum with 4 subintervals. This is going to basically be 2 times 8, 2 times 4, 2 times 5, and 2 times negative 12. Don't let that negative bother you. It's just going to naturally take care of that area that falls below the x-axis. Showing the work in this step is very, very important. Notice I showed it in 2 different ways for these 2 different problems. You can either factor the 2 out and then just add all those heights together, or you can distribute that 2 and do each individual rectangle. Either way is acceptable, but make sure that you show that highlighted step. That's the important part of the problem. These 2 answers are given wildly different estimations for that same integral. It's this negative 12 is not included in that left Riemann sum, but it is in the right. So don't let that big difference throw you. Just follow the procedure. In part C, we're asked to approximate that integral using a midpoint Riemann sum with 2 subintervals. Recall how we found the length of each subinterval. We took the limits, we subtracted them, so 9 minus 1, divided by however many subintervals we want, and that gives us that each subinterval is of length 4. So when I look at my table, my first subinterval is going to go from 1 to 5, so it's going to be 4 units in length, and subinterval number 2 goes from 5 to 9, and it also is 4 units in length. So my 2 intervals, here is one of them, and then the second one goes from 5 to 9. Notice now I have 3 choices for the height of my rectangle. The number on the left, of course, is for your left Riemann sum. The number on the right is for your right Riemann sum. If we're doing a midpoint Riemann sum, we want to choose this point right in the middle. And notice that 3 is midway in between 1 and 5. So the height I'm going to use is 8. Rectangle number 1 is a 4 by 8. So 4 times 8. Rectangle number 2 of my midpoint Riemann sum goes from 5 to 9. So that is 4 units wide. And the 4 is for the left Riemann sum. The negative 12 is for the right Riemann sum. I'm doing a midpoint Riemann sum, so I'm going to pull this height that's in the middle. 4 times 5. And my midpoint Riemann sum is a 52. In part D, I'm asked to do a trapezoidal sum, 4 subintervals indicated by the data. The first thing I see in my data is I have equal subintervals, which means I can use the trapezoidal rule if I want to. My equal subintervals are 2 units in length. That gives me the height of each of my trapezoids. So that's going to be a 1/2 times a 2. I take the first base. The bases are going to be found by the f of x values. So my bases are in this f of x row. I take that first base once. So that would be 6. Plus, I'm going to double each of the interior bases because they're bases to 2 trapezoids. So each of these interior bases gets doubled. So 2 times 8, 2 times 4, 2 times 5. The first base of 6 and the last base of negative 12 are taken only once. And that gives me a trapezoidal approximation using the trapezoidal rule of 28. If you, and we've got 4 very different numbers up here. If we go ahead and average the left and the right together, so 46 plus 10 divided by 2, notice that averages a 28, which matches that trapezoidal sum of 28. So it looks like something more is going on than just a coincidence, because that happened with our warm-up problem and that trapezoidal sum that we did on the front as well. You may already see the connection, but we'll talk about it more in class. We have one more example to go. In this example, again, I have a table of values. I'm asked to do a left Riemann sum in part A with 3 subintervals indicated by the data. And what I see in this data is I have unequal subintervals. So to find this left Riemann sum, I'm just going to have to find each individual rectangle's area separately. Rectangle number 1 is 4 units wide. I'm going to pull the height on the left side, which is that 3. Rectangle number 2 is 1 unit wide. I'm going to pull its height on the left side, which is a 2, so that's a 1 by 2. And rectangle number 3 is 2 units wide from 6 to 8. The height on the left is represented by that 4, so it's a 2 by 4. My left Riemann sum value is a 22. Like we said earlier, the important step is for you to show this. The requirement is products and sums. Part B is asking for a right Riemann sum with 3 subintervals. Rectangle number 1 is 4 units wide. This time I'm using the height on the right side, which is the 2, so it's a 4 by 2. Rectangle number 2 is a 1 by 4. And rectangle number 3 is a 2 by 9, giving me a right Riemann sum approximation of 30 on that one. In part C, I'm going to do a trapezoidal sum, 3 subintervals. I have this question that says, can you use the trapezoidal rule? And the answer to that is because my intervals are not equal, I have 4 units, 1 unit, 2 units, that makes this trapezoidal rule off limits. We can still find this trapezoidal sum, we just have to find the area of each individual trapezoid. 3 subintervals means I'm going to have to use that area of a trapezoid formula 3 times. Trapezoid number 1 is going to extend from 1 to 5. That is the height, so it's got an h of 4 times the sum of the bases, and these are my 2 bases, the 3 and the 2. Trapezoid number 2 has a height of 1 because we're going from 5 to 6. Its 2 bases are the 2 and the 4. And our third trapezoid has a height of 2, from 6 to 8 is 2 units. Its 2 bases are the 4 and the 9. So my final trapezoidal approximation is going to be 26. Again, the important part is all of this. You'll want to make sure that you show all of the calculations. Don't, for instance, just add these together in your head. You want each of those bases to sit explicitly on your paper. So you don't call that a 5, leave it as a 3 plus 2. And even though here we have a height of 1 and you know multiplying by that isn't going to affect anything, still write it here because you want your work to show that you are using a trapezoidal approximation. Also notice if I average my left and my right, I get a 26, which matches that trapezoidal sum. So it definitely looks like there's something going on. Our final part is asking if that trapezoidal sum is an over or an under approximation. Over here on the side, we have what's going on with that. If you have a concave down shape, whether it's an increasing or a decreasing concave down shape, you can see we're missing little parts when we draw those trapezoids. That's going to lead us to an under approximation. And when we have a concave up shape, as indicated right here, whether that concave up is decreasing in nature or increasing in nature, we're going to be including little bits in our trapezoid area that are not technically underneath the curve, and that's going to result in an over approximation. It is the concavity of the graph that determines under or over with this trapezoidal rule. Note that it doesn't matter if your graph is increasing or decreasing. What I see back in the stem of the problem is this is a concave up graph, and whenever I have a concave up graph, this is going to result in an over approximation. This is how you would answer that question, to say over approximation. Your reason, give a reason for your answer, is just this part about saying your f of x is concave down, and that's all you need to say. Good luck with this, and see us if you have any questions.